Swayam Prabha. Digital India. Educated India.
Okay, we have been discussing groups, and in the last class we have discussed subgroups and cosets. So, we will continue our discussion on on cosets and subgroups. We have seen in the last class that the cosets are basically shifted versions of a subgroup. So, if you have a subgroup H of G, then its cosets. So, one can, we took the example of Z, where Z H times Z is a subgroup. So, Z has all the integers. So, for example, 8 times Z has all these multiples of 8. Then its shifted subgroups, a shifted version, one shifted version will be 1, 9, 17 and so on, and this is a coset, right. So, you can shift by different values to get different cosets. So, you can think of what is shown here as 1 plus H, which is 1 plus H, where H is in H. Now, note that you take any element instead of 1, you can take any element from this set and represent it with that. So, 9 plus H, which is a coset of 9. Coset of 9 is the same as the coset of 1. We have seen in fact that you can define an equivalence relation, and then these cosets are the equivalence classes. So, any representative of an equivalence class can be used to say that it is the equivalence class of that element. So, you can say this is the coset of 9, right, and it will be the same set. As a set, it will be the same set. This is same as 1 plus H. So, this also you can see in general that you can take, suppose you have H 1 belongs to G times H, say call it G 1, G 1 belongs to G times H, G 1 is in the coset of G, then this is same as G 1 H. What is G 1 H? G 1 H is nothing but G 1 times H for all H in H, and you can see that you can write it as G times G inverse G 1 H, G inverse G 1 is E. So, this part is E, sorry, G inverse is E. So, we have just multiplied by E, but now this is this quantity is also in H. We have seen that you take two elements G and G 1 in the same coset, then G inverse G 1 is in H, this part is in H. Okay. So, as a result, so G inverse G 1 is in H, which implies G inverse G 1 H is also in H. So, hence this is same as G times H. You can see it is of the form, all the elements are of the form G times some element in H, this whole thing. So, if you have a group, you have a subgroup H, you take its cosets, let us say this is G H, then you can take any element here and G is here, and you can take any other element also, you can call it G 1 H also if you want. Any element can be taken as the representative of that coset, and we can say that that coset is the coset of that element. So, this particular element that we are writing here is called the coset representative that we are taking to define this coset. Now, in the previous class we have seen that cosets are the equivalence classes under some equivalence relation, and so they partition the whole set. But there is more structure in it than general equivalence classes, and let me state that in a lemma here. First of all, we have already proved that left cosets form a partition of G. So, first of all we should say that there is a subgroup H of G, and we are talking about left cosets of H. Then not only that, there exists a one-to-one correspondence, a bijective map between any two cosets, any two left cosets. So, let us prove this. This one we have already seen by showing that left cosets are equivalence classes of an equivalence relation. Now, this one, so let us take two left cosets, let us say G 1 H and G 2 H. Suppose they are not the same, right. Even if they are the same, this will define a one-to-one correspondence. So, let us see. So, this is, we are going to define a bijective map from G 1 H to G 2 H. How are you going to define it? We are going to define it by saying that G, any element here in G 1 H goes to G 2 G 1 inverse H. Okay. So, let us prove that this is a bijective map. First of all, it is one to one. Why? You take any two elements G, let us call it G and G prime, then we will need to show that if f of G is same as f of G prime, then we will show that G is equal to G prime. So, this means that G 2 G 1 inverse, there is a mistake here, this should be G. So, G 2 G 1 inverse G is same as G 2 G 1 inverse G prime, but then we know that in a group you can cancel from left or you can cancel from right. So, this G 2 cancels, G 1 inverse cancels, and we get G equal to G prime. That proves that it is one to one. Now, on to is also very simple. You take any element on the right hand side here, and it is of the form G 2 H. Take any G 2 H, and then we can write this as G 2 H is equal to G 2 G 1 inverse G, G 1. So, this is identity element, we are just inserting it here, it does not change the value. Now, we rearrange using associativity law and say that this is G 2 G 1 inverse G 1 H, right, and this G 1, and then you can see that it is then this term is in G is in G1H, and so this is f of G1H. This is the definition. You see, it is the definition of f of that quantity left multiplication by G to G1 inverse. So, you see that every element on the right hand side is in the image of f. So, it is a 1-to-1 and onto map, and so we have shown a bijection or 1-to-1 correspondence between these two cosets. So, there is a very nice structure that all the cosets have the same number of elements. So, in fact, when you multiply by one particular element G to all the elements here, this is a 1-to-1 map. So, E goes to G and every element goes to some distinct element here, right. So, it is a 1-to-1 correspondence. You can think of every coset as the shifted version of the subgroup itself, and they partition the whole space, and just like what we said in the case of integers. So, this set of multiples of 8, its cosets are the shifted versions and they partition the whole space, whole set of integers. You can also see if you take the 2-dimensional plane, this is a group under addition. You take any line going through origin. So, this is a subgroup of the 2-dimensional plane, and you get many cosets by shifting this line here, here, here. Infinite number of such cosets are there, parallel lines, okay, and they partition the whole 2-dimensional plane, and they have a 1-to-1 correspondence between there is a 1-to-1 correspondence between any two of them. Okay. So, in the case of finite groups, what it means is that if G is finite, then the order of H, the cardinality of H, the number of elements in H divides the cardinality of G, okay, because the left cosets of H have the same number of elements as in H itself, and all the left cosets partition G. So, G can be partitioned into subsets of this size, all subsets of equal size, which is equal to this, right. So, clearly the number of elements in G is a multiple of the number of elements in H. This number of elements in a group is called the order of the group, order of G. This is also a common notation for that, order of G, right. And the ratio for any subgroup, this ratio is called the index of H, index of H in G. So, for example, if you take the group Z18 like Zn, right, it is the set of numbers between 0 and 17, and plus is modulo addition modulo 18, that is the operation under which this is a group. Any Zn is a group under modulo n addition, and you can take multiples of 3, for example, 3Z18, right, which has the element 0, 3, 6, 9, 12, 15. These are the elements. This is a subgroup, and how many elements are there? It has 6 elements. So, how many cosets are there? It has 3 cosets. 3 times 6 is 18. So, there are 3 cosets. So, you can add 1 to these elements and you can add 2 to these elements, and you will get 2 other cosets other than this itself. Subgroup itself is a coset, then you get 2 more cosets. Now, what if you take 5 times Z18, okay, which means you multiply by 5, but when you do that multiply means addition of that element with itself 5 times. So, addition modulo 18, right. So, what will we get? We will get 0, 5, 10, 15, then 20, which is 2 modulo 18, and so on, and all the things that you will get are actually, you can check that you will get the full set is equal to Z 18, and so that is because 5 is relatively prime with 18. So, you will get the full group itself. Right. Now, we have discussed about cosets. Now, we will discuss a very nice and easy process of determining if a given subset of a group forms a subgroup or not. If you are given a subset, if you want to determine whether it forms a subgroup, if you want to do it from the definition, you have to check so many different things. So, instead of that, we will see that there is actually just one property. If you check that, then that subset forms a subgroup. So, here is the property. If G is a group and H is a subset of G, then, and H is not, it is a non-empty subset, then H is a subgroup of G if and only if G H inverse is in H for all G comma H in H. It is also if and only if, another way to check is that if and only if two properties hold, which is G H belongs to H for all G comma H, and G inverse belongs to H for all, let us write it as H inverse belongs to H for all H in H. These two properties hold. If you check that, then it is a subgroup, or you can just check one single property, this one, and we will see that they are actually equivalent. So, proof of this is very simple. Suppose there is a sub. So, first of all, if it is a subgroup, H is a subgroup of G, then this implies these two properties. That is clear, because you take any element H in H, then H inverse must also be in H, because H is a subgroup. Then G is in H, H inverse is in H, so their operation is also in H. So, this holds. Similarly, this holds, and this also holds. So, this direction is clear. The other direction, suppose this one holds, let us see. Okay. So, for 1, if 1 and if let us say this is the second property. So, 1 implies H is a subgroup of G. So, this we can see. First of all, the operation is associative in G itself. So, it must be associative in the subset, because the elements in H are also elements in G, and the operation is associative. Now, we need to check existence of identity, existence of closeness, and existence of inverse. So, by taking first of all identity element, we can take, because it is non-empty, H is non-empty, there exists a G in H. Okay. And so, we can just take G equal to, so H is also equal to G. Then what does this give us? This gives us that G inverse is in H, but we know that G inverse is equal to the identity element. So, identity element belongs to H. Now, Now, we take any element. So now you can take G to be, take any element in H and G to be the identity element. Then what do we see? This property says that G times H inverse is also in H, but which is E times H inverse, which is just H inverse, that is also in H. So, for any H in H, we see that H inverse is also in H. Now, about the closedness under the operation, take any two elements G and H in H. We have just now seen that if H is in H, its inverse is in also H. So, now instead of taking H, we take H inverse in place of H in this property. In this property, we take, in place of H, we take H inverse and apply that property. So, what do you get? That property says G times H inverse, which is H inverse inverse, that belongs to H. The property says this, right. So, again we have taken H is in H, we have already proved that its inverse will then also belong to H. So, we take that element and G and use the property that is given to us, that is G H inverse belongs to H, and then we get this. Now, what is the H inverse inverse? Inverse of inverse is itself. So, it is very simple to prove that, because you take H, H inverse is identity by definition. So, H inverse is inverse of H, but H is also inverse of H inverse, right. So, this implies that G H is in H. So, it is closed under the operation, H is closed under the operation, because we started by saying we take any two G and H in H. So, their operation is also in H. So, this proves that the first property implies that it is a subgroup. Now, this makes it very simple one step check for showing that a subset is a subgroup or not. Now, the same this property can be broken into two parts. One can see easily that this implies and implied by the second property. Why? So, if we have clearly take, so if this is true, we can again use the same process and show that it is a subgroup. First, take this existence of the identity element in the same way, that if it is a non-empty set, H is a non-empty set, so there is a G. So, you take its inverse by this property, it is also in H, and then so G and G inverse are both in H. So, use this property now to say that G inverse is in H, but that is equal to E. So, E belongs to H, and so in a very similar way you can show all the properties. Now, as a corollary of this, one can say that actually check if the group is a finite group, if it is a finite group, then check becomes even simpler. This inverse need not be checked, you can just check this G H belongs to H for every G and H. Why is that? Because the inverse is in the subgroup that follows from finiteness. So, let us see this. So, here is a lemma. If H is a subset of G, H not equal to phi, the empty set, H finite, then H is a subgroup of G if and only if G H is in H for all G comma H in H. So, just this inverse need not be checked. It is not that it will not hold, it will hold, but it need not be checked. So, let us see this. If this holds, clearly this direction still holds from the previous lemma. In fact, the G inverse also is there in H. So, this second property, right, condition this is part of that. Now, the other direction, the other condition is missing, but still because of the finiteness it will be a subgroup. So, let us see this. So, we need to show that if this property holds, then for any H in H, H inverse will also be in H. So, how do we show that? You take its powers, meaning we take the operation of H with itself repeatedly and see what we get. So, we get first H is there, then we take H star H, which is H square, we write it as H square, then H cube and so on, all the powers of H. Now, as we go on, this sequence must terminate somewhere. What does it mean to say? So, why should it terminate? Because H is a finite set. So, it cannot go on giving you distinct elements, all these cannot be distinct in finite sequence. So, somewhere it must start repeating, which means H power I must be H power j for some I and j, and without loss of generality, suppose j is strictly bigger than I. Then what we can say is that H power j minus I is the identity element, because you can. So, one why is that? Because you can write this as H power I times H power j minus I, and you can cancel, this is H power I times identity, this is H power I times this, and so you can cancel H power I from both sides and get this. Now, this can be written as H times H power j minus I minus 1. J minus I is at least 1 because j is strictly bigger than I. So, this is not negative, j minus I minus 1 is at least 0. So, this is identity, and that means that H power j minus I minus 1 is H inverse. So, and this is a power of H as well, and hence this is there in the subgroup by this property. By this property, if you multiply H with H repeatedly, they all belong to H. So, H power j minus I minus 1 also belongs to H, and so H inverse belongs to H. So, this proves that. So, if this holds, then the second property automatically holds. Second property here automatically holds for a finite subgroup, and this situation will come across repeatedly in our context in the course. We will deal with finite groups quite often, and we will see that to prove that something is a subgroup, this property will come handy, the first property alone, okay, will be very useful. Okay, so, we will continue our discussion on subgroups and cosets. So, one very simple result that we will mention here is that if we have any class of subgroups, let us say HIs, where I belongs to an indexing set, these are subgroups of G, a group G, then their intersection, HI, I belongs to I, is a subgroup. How will you prove this? Well, very simple, we just use that single condition that is necessary and sufficient for proving a subset to be a subgroup, right. If you take G and H to be in the intersection, then we will show that G inverse H or GH inverse we wrote, but does not matter. This is also in the intersection. Well, this is very simple because G and H belongs to each of them. So, if you take any HI, take any I, G H belongs to HI and HI is a subgroup. So, G H inverse belongs to HI. Now, this holds for every I, and so this implies that G H inverse is also in the intersection of HI. That is it. So, this proves the result. Now, we will define something new now. Suppose we are given a subset X of a group. Now, we are interested in knowing what are the what is the smallest subgroup of G which contains all the elements of X. So, clearly if you take any element G in X and if X is a subgroup, X is a subset of a group, then all the powers of G, G2, G3 all G power n, because even negative powers should be there, G inverse should be there in H and its powers should be there, identity element should be there. So, all these must also be elements of that H. So, these elements must be there in H. And similarly, if you take any two elements G and H in X, then G power n1 times H power n2 should also be there in H. So, the subgroup must contain all such multiplication of powers of the elements in X. So, that minimal subgroup is what is called the subgroup generated by X, and we define it as following. The subgroup generated by X, which is denoted by this symbol, this is the intersection of all subgroups H. So, that H is a subgroup and X is a subset of H. All subgroups containing H, you take the intersection of all those subgroups. Now, there may be infinite number of them and there may be uncountably infinite and so on, it does not matter, you can still take intersection. So, you can easily check that such an intersection is a subgroup, as we said, right. So, we have proved here. So, this is a subgroup and this subgroup is called the subgroup generated by X. Let us take an example. Suppose so Z is a group, you take the subset 2, 3, this is a subset. What is the subgroup generated by 2 and 3? It is the smallest subgroup that contains 2 and 3, right. So, what is it? Well, one can easily check that it is the it is Z itself, right, because if 2 is there, then all multiples of 2 are there, if 3 is there, all multiples of 3 are there in that subgroup, and then they are relatively prime. So, 1 is their GCD. So, 1 can be written as 2m plus 3n, where m and n are integers. So, 1 will also be there, it is a multiple of 2 plus a multiple of 3. So, it is also there in the, it must also be there in the subgroup, and if 1 is there, then all elements of Z, which are multiples of 1 basically, so must also be there. So, Z is the subgroup. Now, if you take 6 and 9, this subset, what is the subgroup generated by these two elements? Their GCD is 3. So, you can see, so what you can expect is that it will contain the subgroup generated by this will contain the set of elements of the form 6 m plus 9 n, and we have in fact, we are not proving this yet, but we have this will prove soon, but we have seen that this set, when we will prove soon that this subgroup will be indeed this set, but once we accept that this is the subgroup, then we have in fact analyzed a set like this when we prove Bijou's lemma, right, and we have said that these numbers are basically the set of multiples of the GCD of 6 and 9. So, which is to say this is same as 3L, where L belongs to Z, all the multiples of the GCD 3. Okay. So, this is 3Z, or this is also generated by, you can say this is the subgroup generated by the element 3, all the multiples of 3. Now, it is not always true. So, in both these cases we have seen that for 2 3 as well as 6 9, the subgroup generated by them is a subgroup also generated by a single element. In this case it was generated by 1, in this case it is generated by 3, but this is not so for other groups. For Z in fact this is true, but and we will see results about that, but for arbitrary groups this is not true. There are subgroups which are not generated by a single element. For example, you can take the group of rationals, you cannot find one rational number whose multiples give you all the rational numbers. You cannot get one number, real number, whose all multiples give you all the real numbers, and so on. So, these are not groups like that. Now, anyway, for any subgroup, we will now give a result which will say for any subset what kind of, how to generate all the elements of that the subgroup generated by it. So, and in fact we have discussed it briefly already. For any subset X of G, this subgroup generated by it can be written as A1 power n, A2 power n up to An, let us say At power n, where Ai are in X, Ni are in Z, T a natural number. So, what it is saying is that you pick T elements from X, A1, A2 up to At, and this is pick some integers N1, N2 up to Nt, and just raise each of these Ai's with the power Ni, and then operate, multiply them, right, and then you will get an element. So, by all taking such any finite number of Ai's and raising them by certain integer powers and multiplying, I say multiplying, but what we mean is that take that operation in G between them and then you get an element. So, that way all combinations of Ai's and Ni's and T that you can get will give us a set of elements, and that set is in fact the subgroup generated by X. So, the proof that this is indeed the subgroup generated by X is quite simple. First thing is that you need to show it is a set equality, which means you have to show this and you have to show this direction. So, how do you show the subgroup is contained in this? So, you can check that this is a subgroup that contains all the elements of X. So, it is one of the sets in the definition of the subgroup generated by X here H. Okay, the right hand side is one such H. So, the intersection will clearly be contained in the right hand side then, and this is quite easy to see, because you just take A1 to be any element in X and all others, I mean just T equal to 1 and N1 equal to 1 as well, then it says that every element in X is there in this set, and this is a subgroup that you can check again from our single condition to check if any subset is a subgroup or not. So, this direction is easy. This direction that that this is these elements, this is a subgroup of any subgroup that contains X is also quite simple, because all these elements in on the right hand side must be there in any subgroup that contains X, because in any subgroup if A1 is there, its power n, A1 power n1 must be there, if A2 is there, A2 power n2 must be there, and so on. And so, their operation between them also must be there in that subgroup. So, that says that this right hand side must be a subset of any subgroup that contains the all the elements of X. Now, as a special case, one can say a corollary that you take one element G, the subgroup generated by it has the form G power n, where n belongs to Z. We have already seen that this forms a subgroup, right, and anyway now this is a corollary. It is obvious to see that if you, because this set contains only one element, you can only take t equal to 1 and a I equal to that G, and you get this subset. So, sets subgroups of this form are called, so this is called subgroup generated by G, okay. And this type of subgroups which are generated by a single element is called a cyclic group. And these type of subgroups or groups are of special interest to us. They have very nice properties and structure that we will explore soon. So, let us first see some examples. So, as we said that Z is a group, and it is in fact generated by a single element 1. Actually, we should write it this way, singleton 1, but we will often also just simply write generated by 1 like this. So, this is generated by 1, or this is also generated by minus 1. You can see that these all the integers are multiples of minus 1, they are also multiples of 1, but these are all the integers are not multiples of 2 or multiples of 3. So, they are generated by exactly these two elements 1 and minus 1. If you take any subgroup, so 2 times Z, all even numbers, this also forms a subgroup, and this subgroup is generated by 2 and also minus 2. Okay. So, these are cyclic groups, and in fact, now we will show a very simple and but interesting result, which says that, which says what we have already seen through examples, that any subgroup for any subgroup H of Z, any subgroup H of Z, it is generated by a single element. Okay. There exists some H in Z such that H is equal to the subgroup generated by H. Now, the proof is very simple. You just the division algorithm. So, so we need to find an element H which will generate all the elements in H. So, what do we do? So, we are claiming that this. So, what is this right hand side? If you see, it is of this form. Now, G power n, when you operate G with itself, and here the operation is addition, what you get, we write that as 2 times H rather than H power 2. So, what we are saying is that this is H times I, where I belongs to Z, this set. So, what we do is we select an element H in H, take, so let H be the smallest positive integer in H. So, H has, it is a non-empty subset, and it has, suppose it is not equal to just 0. If it is 0, then there is no such positive integer at all, but if there is a negative integer but not positive integer, that cannot happen, because this is a subgroup. So, its negative also must be there, so which is a positive number. So, there will be, if it is not there is a non-zero number, there must also be a positive number in H. So, take the smallest positive number in H. Now, the claim is that H can be written as subgroup generated by H. Why? Now, take any, we will show that if you take any element G in H, it will be a multiple of H. So, what we do is, it is an integer, right. So, G is an integer. So, what we do is we divide G by H. So, G can be written as some q times H plus R, where R is the remainder, and the remainder is in the range 0 to H, less than H. And now, we see that G is in H, we have seen here, this part is in H, because H is in H, and q times H is q times addition of H, which must also be in H. So, that means R, which is equal to G minus q H, is also in H, but we see that R is either 0 or less than H. So, R cannot be positive, because if it is positive, R will be smaller than H, that will contradict the choice of H. H is the smallest positive integer in H. So, R must be 0, it cannot be positive, it must be 0. So, that implies R equal to 0, which means that H divides G. So, what we have shown is that every element in the subgroup is divisible by this chosen element H, which is chosen to be the smallest positive integer in H. In other words, any subgroup in Z is generated by the smallest positive integer in it. It is also generated by minus H, which is the largest negative integer in H. This is same as this. So, what we have shown is that not only that Z is a cyclic group, it is generated by 1 and minus 1, generated by 1 and generated by minus 1 also, but any subgroup of it is also cyclic. Now, this is true in fact for any cyclic group, that any subgroup is also cyclic. So, this can also be proved in the same way. So, I will write it down that any subgroup of a cyclic group is cyclic. So, again the proof follows by saying that suppose H is a subgroup of G and G is a cyclic group, which means it is generated by a single element, that is a G. So, these can be written, all the elements in G are powers of an element. So, if H is generated is only 0, then we say that it is generated by 0, then done. But if H has some other element, right, then it must be a power of G. Now, if there is a negative power of G, its inverse will be a positive power. So, there must be at least one, if H is not equal to 0, there is an element g power some positive power for n greater than 0. There is some positive power of g in H. So, take H to be g power, let us say L in H, such that L is the smallest positive power of G in H. Then the proof proceeds as before, as here. So, we basically now claim that you take any n such that g power n is in H, then this will imply that L divides n. So, proof of this claim, it follows the same way, that n can be written as q times L plus R, where R is in the range 0 to less than L, and then we take R equal to n minus q L. But then you see that g power R is g power n minus q L, and g power n is in H, and g power q L is in H. So, g power n minus q L will also be in H, but R cannot be a positive power because R is less than L. So, R must be 0, R is 0. That proves the result, that any subgroup is generated by that element which is the smallest power of G in smallest positive power of G in H. So, this proves that any subgroup of a cyclic group is cyclic. So, you can take so again let us say Z18, right. You take any, so this is also a cyclic subgroup, a cyclic group generated by 1. You can get all the elements by adding 1 to itself again and again repeatedly, and all its subgroups are cyclic. And the subgroups, remember, the order of the subgroup must divide the order of the group itself, which is 18. So, the cardinality or the order of the subgroup must be a factor of 18. So, they can be either 1, in which case it is only the identity element, 2, 3, 6, 9 and 18, which is the full group. So, these are the possible orders of the subgroups of Z18, and they are generated by which elements? So, in case of 1, it is the identity element 0 itself. 2, what is the subgroup of order 2? Well, 1 and 9, 0 and 9. This is subgroup of order 3, 0, 6, 12 and so on. Okay, so we will continue our discussion on subgroups in the next class.